All right, so I just wanted to do a bit more about vector fields for a few minutes. So I went over an example of a vector field. I like to go over this vector field in 2 dimensions. It is defined by simply x, y. Okay, so if we plot a few points to try to see how this vector field works. All right, so let's say again at 0, 0, we get the vector 0. At, let's say 1, 0, we get the vector 1, 0. Basically here, the I hat component of the vector field is the same as x, and the j hat is the same as y. At point 1, 1, we get the vector 1, 1. At point, let's say negative 1, 0, we get the vector negative 1, 0. All right, now if we increase the values of x and y, let's say at 2, 2, we get the vector 2, 2. Notice that the components of the vector field get bigger, so the magnitude of the vector field also gets big. You can also find the magnitude of the vector field. You can find an expression for the magnitude of the vector field. So here are some of these vectors. At 0, we just have that point. Again, at point 1, 0, we have this vector that has a magnitude 1. At point 1, 1, we get this vector. Now, at point negative 1, 0, we get the vector negative 1, 0, which is pointing away from I hat. Okay. Likewise, at negative 1, 1, you get this vector pointing away from the center. Okay, so I'm going to draw some more vectors, although I did not find these vectors in the table. And say here's the vector 2, 2. So again, vector 2, 2 has a higher magnitude. And if you draw more and more of these vectors, you could see that all the vectors are pointing away from the center or the origin. And again, the magnitude of this vector field is square root of, just square these and add them. And that gives you square root of x squared plus y squared. So again, as x and y increase, the magnitude of the vector field gets big. So as you go away from the center, again, you're looking at vectors that get larger in the magnitude. Okay, let's look at a couple of more vector fields. The vector field in 2 dimensions given by negative x, negative y, x. Okay, this particular vector field that I just did is called the position vector field, because x and y, x comma y, is the position, is just position of a point. Okay, and again, the components are just same as x and y here. So they call this, again, the position vector field. All right, now let's draw this vector field without plotting points, actually. Okay, so notice that if you compare this vector field to the position vector field, the components are switched and one component is negative. So you could say that this vector field and this vector field are orthogonal, right? If I do negative y comma x, dotted with the previous vector field xy, we get 0. So what you can do is you could draw this vector field and then draw vectors orthogonal to basically every vector here. That's one thing you could do. Let's try that actually. All right, so let's say we have the vector 1, 0, we have the vector 1, 1, we have the vector 0, 1, negative 1, 0, 0, negative 1, also negative 1, 1, negative 1, negative 1, and 1, negative 1. So this is the previous vector field. All right, now drawing this vector field, let's just plot 1 point. Okay, so let's say we do this at 1, 1. You get the vector field negative 1, 1. Negative 1, 1. If you draw that, so at point 1, 1, which is this point, we get the vector negative 1, 1, meaning that you go left by 1 and you go up by 1. Okay, so we end up with this vector. Okay, likewise, if you plot the point 2, 1, we get this vector, which is perfectly orthogonal to this vector. So the blue vector field is the new vector field. And this is an example of what they call the rotational vector field. Obviously, there is a rotation. All right, so if someone falls in, they will basically rotate until they sink. All right. Next, we are familiar with a kind of a vector field. There's a vector field that we have seen in the past that we worked with, but we never called it a vector field. Remember the gradient of a function. The gradient of a function is a vector whose components are functions of x and y. They were the partial derivatives of the function. So for z equal to f of xy, the gradient of f is the partial derivative of f with respect to x, partial derivative of f with respect to y. And again, we have a vector field here. You can call this capital F of xy. Okay, so this particular vector field is called the gradient field. And because again, it's just the gradient of a function. So what does that mean? What does a gradient field do? Let's look at an example of a function that we are all familiar with, the paraboloid. Okay, whose gradient is gradient of little f, which you can again think of it as the vector field capital F, if you want to call it that. It's just 2x 2y, those are the partial derivatives. And this gives you a vector field in 2 dimensions. Okay, now, what does this vector field look like? This vector field is just twice this first vector field, right? So vectors are going to all point away from the origin. Okay, now why does that happen? Well, how does this relate to a paraboloid? Or not the, is that right? Yes, paraboloid. How does this gradient field relate to the paraboloid? So remember that the level curves of this function, the paraboloid. So we have the paraboloid, and at each level of z, the level curve is a circle. Okay, it's just a circle of radius, say c. The level curves are circles. And let's just draw some of these level curves in 2D. So looking from above, if you have traced the level curves or drawn the level curves on the paraboloid, this is what you see. I am going to get rid of the shade. Okay. What do we know from chapter 15? We learned that the gradient vector is orthogonal to the tangent line to each level curve. The gradient is basically orthogonal to the level curve. Okay, so this would be one of the gradients, right? This would be another gradient, right? And if you draw another gradient, right, it will be orthogonal to this level curve. This would be another one. Gradient is orthogonal to the level curves. And this is exactly what they call the radiating vector field, because the vectors are radiating away. It's just like the position vector field that we did earlier. All right, so the relationship between the gradient vector field and the level curves. All right, so the next thing is the definition of what we call the conservative vector field that we are going to talk a lot about in section, I believe, 16.3. A vector field is conservative if it happens to be the gradient of some scalar function. Okay, so this means that f is conservative basically if there is a little function, right, little f of xy, such that the vector field capital F is the gradient of this scalar function, little f. Okay, so if you can find a function f of xy whose gradient is your vector field, then you know the vector field is conservative. Okay, so for example, z equal to, or actually, let me do it this way. The vector field 2x, 2y is conservative because this vector field is the gradient of x squared plus y squared. Okay, and this idea is kind of important when we do line integrals or when we find the work that is done by a vector field to move a particle from one point to another point. Okay, so this idea will be used later on. All right, so a question could be asked in section 16.1 to find a conservative vector field all right, if you don't mind, I'm going to abbreviate vector field using VF that has the potential function f of xyz equal to x squared plus 4y squared plus 16z squared. So what is the potential function? Now, if you have a vector field that is conservative, meaning that, again, it's a gradient of some scalar function, this scalar function is called the potential function. Maybe I add that to the definition. Okay, so little f is the potential function. All right, so for example, for the previous example, x squared plus y squared is the potential function. So for this problem, for the new example, you're given the potential function of the vector field, and you want to come up with the conservative vector field, which is basically the gradient of this vector field. So capital F, which is the conservative vector field you're looking for, is the gradient of this potential function. And the gradient is the partial derivative with respect to x, then the derivative with respect to y, and then derivative with respect to z. This gives you a vector field in 3D. And in 3D, this is also, so this is the gradient of this potential function, which is a function with 3 independent variables. This function has level surfaces, if you remember, okay? And this vector field happens to be orthogonal or normal to those level surfaces. All right, and if you attempt to draw this vector field just like the previous vector field in space, the vectors are going to point away from the origin. Okay, it is like you are getting away from the origin in all directions. All right, and that's because the level surfaces of this thing are ellipsoids, right? The coefficients don't match. If they did match, you have a sphere, but we have ellipsoids. And if you draw normal vectors to the ellipsoid, it is going to seem as if those vectors are getting away or radiating away from the origin. Okay, a couple of last things about vector fields. A vector field is a vector, okay? At each point in space, we have a vector. And there are certain things that certain operations that we learned about vectors, like vector addition. We had special multiplications. There are two operations that can be done on a vector field. And one of them is called the del of a vector field. Okay, so the del is an operation. Let me go to the next page. Okay, so this is the del operator. An operator is an action on something. For example, we have in calculus 1, the derivative operator, the ddx. What does ddx do? When you put ddx in front of something, in front of a function, it takes the derivative of that function. Okay, so the del operator is a vector form of the derivative operator, and it's denoted by basically the del notation, and it is the vector whose components are the partial derivative operators. Okay, now this vector doesn't have a value. It doesn't have a value. You can't really draw this vector or quantify this vector. This is a vector, but it is, again, it doesn't quantify. Okay, it does, the del vector does something to a function. Okay, so for example, as we know, the del operator acting on a scalar function, this is in 2 dimensions. It could also be in 3 dimensions. It gives you, let's see, so we have the partial derivative operator with respect to x and y as a vector. This acts on f, and it gives you the derivative of f with respect to x, the derivative of f with respect to y. It seems as if this is being multiplied by f. That's not correct. It's acting on f. I know this is a little weird, but again, this vector is not really a vector that is measuring anything. So what does this give us? It gives us the gradient of this function. Okay, del acting on a scalar function gives you a gradient of the function. Now we have 2 more operations. We have 2 operations that we need to learn about for chapter 16. These are just operations. like the derivative operation. One of them is the curl of a vector field. Okay, so again, a vector field is a function whose outputs are vectors. And there is this new operation that we are going to define that is done on these vectors, on the vector field. And one of them is called a curl of a vector field. I know this kind of sounds fancy. This is basically the del operator crossed with the vector field. We write this as curl of f. Okay, curl of f is the del operator crossed with the vector field. So what does it look like? It is the del vector, which has those partial derivatives operators crossed with the vector field in 3 dimensions. Let's say the vector field has elements P, Q, and R. Okay, these are functions of x, y, z. So this, in reality, this is P of x, y, z. We have Q of x, y, z, and R of x, y, z. So what does this look like? You take the determinant okay, you put the operators in the second row, and you put those functions in the third row. Here we have P, Q, and R. Okay, so let's see how this works out. If you're going to evaluate this determinant, right, you begin by ignoring that column. We do the partial derivative of R with respect to Y. Okay, minus the partial derivative of Q with respect to Z. That's what it does. So for example, let's say that we have a vector field that's given by 3x, y, z squared. This is a 3-dimensional vector field. We have y squared sine of z and x e to the 2z. All right, and we want to find the curl of this vector field. Okay, so again, we write it as del cross f. Let's set this up. All right, second component. Each is a function of x, y, or z. And last component, xe to the 2z. All right, so you just have to be careful. All you're doing here is to take partial derivatives, just like as you do the cross product. Okay, so ignore that column. We have the derivative of xe to the z with respect to y, right? But xe to the z has no y in it, so its derivative is really 0. Minus, we do the derivative of y squared sine z with respect to z. Here we do have a z, so y squared is constant. The derivative of sine z is cosine z times that by y squared. We have y squared cosine z. All right, so just again, like a regular cross product, we need minus here. We got now the derivative with respect to x of e to the 2z. Right, so here again, we have a x. So e to the 2z is constant. The derivative of x is 1. Therefore, the answer is e to the 2z. Minus, we have the derivative with respect to z of 3xyz squared, which is 6xyz. All right, and then finally, we do cover the third column, and we do the derivative with respect to x of y squared z, which is 0, minus the derivative with respect to y of 3xy z squared. So the derivative of y is 1. We get negative 3x z squared. Yes, so that is the this is the curl of the vector field F. So what does the curl really do? It measures what the name says. It measures rotation in a vector field. And again, these operations are supposed to be taught later on in chapter 16, but I thought that I should go over them now and just get it over with. But we're going to study what the curl does more. But again, what it does is that it measures the amount of rotation, okay, in a vector field. Okay, so imagine we have a vector field that has some rotation in it, right? And let's say you're finding the curl at a certain point. The curl happens to be, imagine we have, again, this is a two-dimensional vector field. Just think about it. If this is a two-dimensional vector field, then the curl is going to stick out of the vector field. Okay? And the stronger the rotation, the longer the curl vector. The curl is itself a vector, the longer that curl will be. If there is no rotation in the vector field, the curl is going to be 0. So that's what the curl does. Again, it just measures the amount of rotation. Okay. All right. We have one more operation for the vector field. I'll go over that now. This is called the divergence of F. The divergence. So we have the curl of F and we have the divergence of F. This is defined as the del operator dotted with the vector field. So this operation is actually a lot easier to do. And what you do is just take the del operator, which is again the derivative in vector form. And you dot it with the vector field, PQR. Okay, so what does this action do? You do the partial derivative of P with respect to X And then we add the partial derivative with respect to y of q, add to the partial derivative of I with respect to z. Okay, so for example, let's say we want to do the curl of the vector field, let's say x, y, z. Did I say curl? That is the divergence, And you can, by the way, you can write that as div f. The divergence of f is denoted by div f. So the divergence of the position vector field x, y, z is, again, write down the del operator. You want to dot it with x, y, z, which gives us the derivative of x with respect to x. That's 1. The derivative of y with respect to y, and z with respect to z, they're all 1. So we get 3 as the divergence of f. Okay, and again, we're gonna learn about these operations later on, what the divergence does. The divergence of a vector field has to do with the measurement of the flux due by a vector field. What is flux? Flux is the is how fast things will flow out of say a surface, and in this case that's due to the vector field. And again, it's something that we're going to learn a lot in learn in more details in chapter 16.